So students, we are still at economic application part 1, where I'm basically solving problems in terms of optimization with one choice variable or single variable. So I'm going to cover now 4.23 from the same very chapter. However, this math is a little bit different from the ones I have already showed to you. And here you can feel the connectivity with the economic concepts and optimization better. So that's why I have chosen this example. So I will describe the question definitely for you, but let's see what does the question provides us with. So it is actually providing us with two equations, a total revenue equation, which is 1400Q minus 7.5 Q square. And it has also given us a total cost equation, which is Q cube minus 6Q square plus 140Q plus 750. And it has also asked to use the marginal concept to solve for the critical value. That means it has asked us to use the condition MR is equal to MC to solve for the optimal Q. What is this optimal Q? This Q will determine profit is maximized at what quantity. So now, number one, what is the question asking for? Given the total revenue, total cost function, it is asking to maximize profit and identify the critical value, which I have mentioned as the optimal value over here. And in order to do that, we are going to use this MR is equal to MC condition. So this is the profit maximization condition under perfect competition to identify the optimal quantity. Then we need to also test the second order condition to identify that whether profit is maximized or not. And finally, we need to calculate the profit amount. Now from here, how would I get, or how would we get the MR and MC? I think you should remember from your Eco 201 concepts, or even the concepts that your instructor Tanvi Sobhan has covered in previous chapter. So from there, you should remember that your total revenue is nothing but, if we take the first order derivative, that means dTR by dQ, it will provide you with the marginal revenue. In other words, this is basically the first order derivative of total revenue. So that's from where we are getting the marginal revenue. And given the total cost, if you differentiate the total cost with the given quantity, you get the marginal cost. So again, this marginal cost is basically the first order derivative of total cost. Now, keeping these two conditions in mind, let's solve for the first order condition. So given TR is equal to 1400 Q minus 7.5 Q square, if I'm taking the first order derivative, that means this is equal to MC also, and I'm getting 1400 minus 15Q. Similarly, in terms of total cost, the equation is Q cube minus 6Q square plus 140Q plus 750. If I take the first order derivative, I get, oh, my bad. I have mentioned here MC in the previous one. It shouldn't be MC, rather it should be MR. Please correct here, it should be MR. Because by differentiating total revenue, we can only get marginal revenue, and we can never get a marginal cost. I'm extremely sorry for this mistake, because you don't do that. Okay, take a note, correct it. Now let's come back to the total cost. So total cost, if we differentiate it once, as I was saying, that eh, it will provide us with the marginal cost, and this is simply then equal to 3q square minus 12q plus 140. Now let's equate these two equations to get the optimal level of q. Okay, so taking mr is equal to mc in mind, we are writing that mr is 1400 minus 15q, mc is 3q square minus 12q plus 140. If we solve for it, I'm just skipping one step, do the calculations by yourself. So our reduced form would be 3q square plus 3q minus 1260. Okay, and from here we can take 3 in common, reduce it more, q square plus q minus 420, which is equal to 0. Okay, if we put it in middle term factor, we get q square plus 21q minus 20q minus 420, which is equal to 0. Okay, now from here, let's take common. Okay, so if you take q in common, you will get q into q plus 21 minus, if you take a 20 in common, you get q plus 21, which is equal to 0. Or we get q plus 21 and q minus 20 is equal to 0. So the two critical values we have got here is negative 21 and positive 20. So these are what? These are the critical values. Now this is for the first time we are getting two different critical values. Obviously the reason is we have a quadratic equation over here, so we'll be getting two different critical values, but this is a new case for us. We haven't seen two critical values so far. Now in such a situation, how to decide which quantity is actually maximizing the profit? So for that we need to do the further exercise. We need to look through the sufficient condition, and over there it will help us to identify whether profit is maximized or not, and for which quantity it is actually being maximized. Now as the first order condition of total revenue provided us with 1400 minus 15q, so if we differentiate it, so this was the first order partial derivative, right? So if we differentiate it with respect to q again, we get a negative 15. And the total cost, which was differentiated once, we got 3q square minus 12q plus 140. So if we differentiate it twice, we will simply get a 6q minus 12. Now, if we are asked to identify whether profit is maximized or not, from this condition we cannot conclude, or we cannot actually tell the final result, but rather we need to form a profit equation. My bad again. So I'm erasing this and I'll be doing it in a fresh page. So in order to identify the profit, that's what we need to do. We need to subtract the total cost from the total revenue. Okay. So what we are doing here is taking profit, and which is total revenue minus total cost. So then what we do, we plug in the values. So differentiated twice in terms of total revenue, we get a negative 15, and differentiated twice in terms of a total cost, we got 6q minus 12, right? Now, if we work on this equation, we finally get a minus 15 minus 6q plus 12, which ultimately provides us with a minus 3 and minus 6q. Now, this is your profit equation. Okay. Now, in this equation, in this very equation, now you plug in the value of q. Okay. So if we do that, then what happens? Profit is negative 3 minus 6q. Now, if you're taking q is equal to 20, what do we get? Then we get a negative 3 minus 6 into 20 will provide us with a 123, which is less than 0. That means the profit function is at its relative maximum, and it is at its relative maximum, and it is concave in shape. So for what quantity? It is for a q is equal to 20. We are getting that profit is maximized. Let's see what happens in terms of when we take q as 21. So if we take q as negative 21, the value that we have identified just a while ago. So this is negative 3 and 6 into negative 21. So finally, we are left with a negative 3 and a plus 126, which gives us 123, which represents it as greater than 0. So now the profit function is not maximized because it is at its relative minimum and it is convex. So finally, we can see that at q is equal to 20, profit is maximized, and at q is equal to negative 21, profit is not maximized. Okay, so in that situation, what is the quantity that will maximize the profit? It is q is equal to 20. Finally, you can always calculate the total profit amount by plugging in the value in the equation. Okay, so yeah, that's it. We will be stopping here, and I have tried to cover different categories of optimization with one choice variable or single variable. You go through the book, you will find many more examples. Practice all those. If you face any problem further, you can always consult us during your live sessions. But before that, I would really appreciate if you go through the concepts, go through all the economic applications, and then come up with some real problems. So thank you for watching this set of lecture. I'll be moving towards the concept of optimization with two variable in the next lecture video. Keep watching. Thank you.